Hi there. In this video, we present our work, PhotoWCT2, compare autoencoder for photorealistic style transfer resulting from Blockwise training and high-frequency residuals. Photorealistic style transfer is an image editing task to render a content image and the style from a style image. Meanwhile, the resulting image should look realistic. Models for photorealistic style transfer are based on autoencoders. Here is the basic model, where the encoder is the pre-trained BGG19 network from the input layer to the value for one layer. We use the encoder to extract the features of content and style images. Then we apply the ZCA feature transformation to adapt the content feature to match the covariance of the style feature. Finally, we use the decoder to invert the transform feature back to a stylized image. State-of-the-art models, PhotoWCT and WCT2, extend the basic model to use multiple feature transformation for more aesthetic results. PhotoWCT implements coarse-to-fine feature transformations to sequentially adapt the coarse value for one content feature to the fine value one content feature. This results in strong stylization strength, but the implementation uses an inefficient cascade of 4 autoencoders. On the other hand, WCT2 is based on an efficient single autoencoder. However, it results in weaker stylization strength than PhotoWCT due to the use of fine to coarse feature transformations. In addition, it introduces wavelet-based skip connections to reinforce the construction of high-frequency details, but this kind of skip connection is computationally heavy. We propose a new single autoencoder model, which we call PhotoWCT2. Our model is a redesign of PhotoWCT, and so it has strong stylization strength. Unlike WCT2, our model uses computationally light skip connections, which we call high-frequency residuals, for better high-frequency detail reconstruction. To implement the coarse-to-fine feature transformations of PhotoWCT, we have to make the decoder to reproduce the value N1 features from the encoder. Rather than using end-to-end training to train the decoder to reproduce the features at once, we propose Blockwise training to distribute the training load. To this end, we first split the encoder and the decoder into blocks. First, we train the first decoder block to reconstruct the input image. Next, we train the second decoder block to reproduce the value 11 feature by minimizing a feature reproduction loss. Since the 4 blocks in the red box should be an autoencoder, we minimize the image reconstruction loss. To boost image reconstruction, we also minimize the perceptual loss. Next, we train the third and the fourth decoder blocks similarly to how we train the second decoder block. At the end of training, the decoder should be able to reproduce the value N1 features. However, Blockwise training may fail if without proper skip connections. Moreover, skip connections using existing photorealistic style transfer models are insufficient since they are either lossy or computationally heavy. We propose high-frequency residuals to address these issues. Recall that Blockwise training aims to reproduce the encoded feature F at the counterpart layer of the decoder. To make it possible, we average through the feature F to derive a low-frequency feature FFEG and skip connect the high-frequency residual of F, which is the difference between F and the upsample FFEG. Since FFEG, which is the low-frequency part of F, can be easily reconstructed by the decoder block, and the high-frequency residual supplements the high-frequency part of F, F can be reproduced at the decoder. Here are results from different models. Our models are the most lightweight, the fastest, able to handle the 4K resolution, preserve good image quality, and have strong stylization strength. Compared to the end-to-end training, Blockwise training results in slightly stronger stylization strength. This is due to the lower feature reconstruction losses of Blockwise training. This evaluation study shows that high-frequency residuals enable Blockwise training by producing lower reconstruction losses. We can visualize the better image reconstruction of high-frequency residuals than other skip connections. In this work, we designed a compact autoencoder for photorealistic style transfer to achieve better performance than existing models. Thank you very much.